Good morning, Thermo 1 class. It's actually Sunday morning, November 1st. I'm going to record 40 minutes of lecture. This will be our first discussion of Chapter 8 on the Rankine cycle. We're not going to have class on Tuesday at the regular time. I have a conflict. But between this and I have also posted video of the solution to number 2, so you can watch that at your leisure. Okay, so reviewing the schedule, we see that right now this lecture is for the 3rd, Tuesday, so let's discuss chapter 2 and start chapter 8. So we're right on schedule. We're right where we need to be. So we have this discussion on chapter 8, and then we have 1, 2, 3, 4 more classes. So we have lots of time for chapter 8, and then we jump to chapter 10, where we have 3 classes of review, and then we're looking at the final exam on December 7th. So we're a good 2/3 the way through class. Anyway, let's get moving. Okay, so this is the lecture. I've changed the name. I use these slides in the steam power plants class as well, but it does. We do a review of the Rankine cycle. And now this you won't find in your textbook. We're not going to spend much time on this, but this is an actual thermodynamic cycle for one of the 2 sized units at the Kingston steam plant. These are coal-based units. These things are still in operation. A lot of the coal units are shut down, but Kingston continues to operate. I would say they'll probably be there in another 3 to 5 years, something like that. Coal is on its way out as an energy source. It's just that we have so many generating units across the country that it's going to be a while before the country can get completely off of coal. But at any rate, the idea here was to let you see what the actual cycle looks like at large scale power at 150 megawatts, which actually is small by utility standards. But you see, we have a boiler here. Let's see, this is the main steam line. It's almost 1,000,000 pounds an hour. Pressure, the absolute 1815, so 15 for atmosphere, 1800 psig, 1,000 degrees Fahrenheit. And they even give you the enthalpy on the diagram. This is BTUs per pound, 1480.3 BTUs per pound. Goes into a high pressure turbine. We come out, we have all these extractions. These are extractions where steam goes partially through the turbine and then it's pulled out. So the first extraction, you come down here and it goes to feed water heater. And we see that's 47,000. That's at 710 pounds. That pound sign is pounds per hour. I believe is the temperature. So that would be 719 degrees, and the enthalpy is 1360, something like that. I think I'm reading it right. So at any rate, we have feed water heaters, 1, 2, 3, 4, 5, 6, 7 feed water heaters. Okay. Here's our main boiler feed pumps. They're pulled. This is the aerator or the open feed water heater. We have to have one open feed water heater to help strip oxygen. These are all turbines. We go back to the boiler, as we'll see. This is the reheat. After we go through the high pressure turbine, the steam is not extracted at 1 or 2, goes back to the boiler, goes back 640.2 degrees and comes back out at 1,000. And notice we do have a little bit of a pressure drop, 450 coming out of the turbine, and we're 405 going back to the intermediate pressure. So this is real data for us. So it has some stray heat transfer built into it and all that sort of thing. Here's our generator. This finally our low pressure turbine, and this is our condenser. There's our generator, etc. So you can look at this. You can pause and look at it as much as you want. I just kind of wanted you to see what a real cycle is. And this is the real cycle for the larger unit. Kingston has 150 megawatt design units and 200 megawatt design units. And so you see it even gets a little more complicated. It has 8 feet water heaters. Here's the boiler over here again. Here's high pressure turbines, extraction stuff. Now, if you actually go to work in the power industry, this is the amount of complication that you get to deal with, or nobody's responsible for the whole cycle. Okay. So I wanted to make a few comments on where in the U.S. what fuels contribute to our electric generation. And what this slide is showing is this is the percent share at whatever point in time. And so I'm not sure how often we recalculate it, whether it's monthly or weekly or daily or whatever, but they compile statistics. This is the U.S. Energy Information Administration. They have a big website and they have all kinds of statistics about energy consumption, not only in the U.S. but around the world. It's typically called the EIA, and it's a good website to go look at. But it's a large site. There's all kinds of information. But we see, and let me turn this pointer on. This arrow option. Keep that guy on. So all the way back to 2008, midway through, looks like 2019, I guess. I'm not sure if this is 19, 20. So anyway, February and March in here, they make the note that in March, renewable share generation exceeded coals for the second month in a row, pushing them ahead of coal for the entire first quarter, which is pretty remarkable. As recently as 2008, coal share was above 50% in January, February, and March. Renewables include utility scale solar, wind, and hydro, which would be dams. A lot of power gets generated by TVA. The dam backs up the water, and then you let the water with all that pressure behind it go through a turbine, turn the generator, and we get absolutely emission-free power from that. But you can kind of see the trends. You can see how renewables are increasing, coal drastically decreasing, and natural gas is increasing. A lot of the decreasing coal has been made up with natural gas. We call those combined cycles. And if we have time, we'll have a slide or two to do some discussion on that. That's the gas turbine cycle coupled with a steam cycle as well. So let's see, we got nuclear, and so they got hydro included with renewables. You can see nuclear just maybe has increased a little bit, but when you have nuclear, you usually base load it because the fuel is cheap. The plant is very expensive to build, and so once you have that asset, you're going to run it pretty much to the maximum. Okay, and so I think that's enough. But we can see things are changing in the power industry. I mean, it's such a massive amount of equipment. These plants are so huge, so costly. It takes a while for it to change, but things are definitely moving away from coal towards natural gas and renewables. Okay, so if you look at total generation by fuel source, now, see, these are percents, but so it doesn't really give you any idea of the total. And I will say also, the percent of renewables goes up, say in the spring and fall, because the total amount of power produced. In the heat of the summer, the cold of the winter, the demand for electricity is much higher. So the renewable share goes down as a percent because we're running all the renewables we can just about all the time. Because once you build that stuff, you want clean power. Okay, so when we look at totals for a year, and this data usually lags by several years. It takes them a while to get this out. This was the most recent comparison. Line that compares. Again, it's the EIA, and we can see in 2010 versus 15, and we know from that previous slide that these trends are continuing, but we can see that, for example, natural gas is the red here, 22% in 10, 31%. Coal from 44 down to 30. For years, I mean, back in around 2000 and all, coal was way more than 50%. So you can see it's shrinking. And this is rapid for the power industry. Nuclear, again, hangs in there. We've had a few plants come online, but after they get old enough, they have to take them off and decommission them. And so, relatively speaking, nuclear has stayed about flat. It's extremely expensive and time consuming to build a nuclear plant. Lots of regulation, red tape. So, I'm not sure how many. We haven't actually started a brand new nuclear plant in this for, I think, quite a while. Seemed like South Carolina had attempted to start one, and I think they mothballed that project after a while, and the ratepayers took a couple billion on the hit. I'm not positive about that, but I think that's right. Let's see, renewables have almost doubled, 5 to 9%. Conventional hydro, it's going to stay about the same. We're not really building any new dams. It's just really a function of the rainfall. We get a lot of rainfall, we have more water back up behind the dam, we can get more hydro out of it. And petroleum products, we, I'm a little surprised to see that net U.S. generation. So this does look like electric. Don't know. Usually you see the oil, petroleum numbers pretty much flat because oil is pretty expensive. So I don't think that's a continuing trend, frankly. But anyway, you kind of see the big trends are more natural gas, way less coal, nuclear pretty stable, hydro, hangs in there, place between 45 and 10%, depending on rainfall. And nuclear is pretty flat. Okay, so one more slide on general discussion here. To meet our national power needs, there are challenges related to. Your authors point out declining economically recoverable supplies of non-renewable resources. Well, I don't know that I agree completely with that. Because of the advent of fracking and directional drilling, the U.S. Now leads the world in the production of oil and natural gas, and prices, our natural gas prices are extremely low. So, years ago, we used to just say, oh, well, the stuff was expensive. I mean, gas is now being sold $3 to $4 a million BTUs. I remember a time when it was, at least 8 to 10, if not 12 to $14. That's what fracking and direction have done for us, which has also reduced emissions because the power companies can now afford to generate with natural gas instead of coal. That has led the switch and shutting down of a lot of coal plants, which is positive. A coal plant for the same electric generation, the coal plant is going to put up roughly twice as much CO2 as the natural gas plant. Okay. Oh, what do we have? Effects of global climate change and other environmental and human health and safety issues. Our plants are extremely clean these days. Now, the global climate change, there are differences of opinion on this, and I'm not going to get into this. I'll just say that in some cases I am skeptical, not about the whole issue of climate change, but how much impact that the activities of man and the emissions of power plants have directly on the climate. I expect there is some impact, but whether it's as significant as a lot of people claim, I don't know. I'm skeptical. It could be true. It's really not my area. I just have an opinion like everybody else. Okay. Health and safety. I mean, if storms and such, if you're going to blame those on the power industry per se or something like that, then perhaps. But as far as safety, the emissions, particulates, and all that sort of thing that would do particles that could get in the lungs are pretty well. I know most industrial companies that I've ever worked with are very, very conscious about their environmental impact. But that's not to say that there certainly is rapidly increasing demand for power owing to increasing population. Well, now worldwide, that's certainly true. In the U.S., our population is fairly flat. We may be moving slowly, but not nearly at the rate of perhaps India, China, and other very populous countries around the world. And today, we are still dependent on coal, natural gas, and nuclear. Well, that's certainly for sure. And there's another little pie chart. That's 2016. So on this one, you can see natural gas. You have 33%. That's coal, 30%. Nuclear, not quite 20. Hydro, etc. So you can see that's pretty similar to the numbers that we had in 2015 on that previous slide. But this is the end, and renewables are sort of growing rapidly, and they will continue. About this part of the country, we don't see a lot of wind farms. We go up north through Illinois, and then to the Midwest, and they do have massive wind farms. Okay. Introducing power generation, coal, natural gas, and nuclear will continue to play important roles. Contributions from wind, solar, and other renewables are increasing. So what this table, and this is out of your textbook, shows is it looks at the power plant type, coal, fuel, natural gas, nuclear, oil, etc. And it notes whether it's renewable or non-renewable. And then it names the cycle if there's one that the plant operates on. And so you see the coal-fired plant is a Rankine cycle, nuclear Rankine, oil Rankine, biomass fuel Rankine, geothermal Rankine, solar concentrated. Rankine shows up. That's why we're going to spend a lot of time on the Rankine cycle. Brayton cycle is a simple gas turbine cycle. A lot of the natural gas plants these days are a combination. It's called a combined cycle plant, and it's a Brayton cycle, and then the hot gases feed into a Rankine cycle where it steam is generated. So we'll have a little time to look at that as well. And then we get down here to most of the renewables. Hydro, no, I mean it's just water flowing through a turbine, so it's not a cycle. Wind, wind, pushes the blades on the windmill, it turns generator. Photovoltaic, that's semiconductor type material. Fuel cells, non-renewable cycle, and then we have their devices they can put out in the ocean, which some people consider pollution. And as the waves roll in, they knock something back and forth, bobs up and down, and you can generate power out of that. So we probably won't spend this time on some of those last devices. Not the purpose of thermal. Not a large topic for us. Okay, introducing vapor power plants. Let's see. So four components of four alternative vapor power plant configurations are shown. So we're going to look at a diagram for fossil fuel vapor power plants, pressurized water reactor vapor power plants, concentrating solar thermal vapor power plants, and geothermal. In each of the four types of vapor power plant, a working fluid is alternately vaporized and condensed. So when we use the term vapor power plant, we're talking about boiling and condensing whatever the working fluid is. And we can have different fluids used. Key difference among the plants is the energy required to vaporize the working fluid. And there are cycles out there for heat recovery that are termed organic Rankine cycles. They're a simple Rankine cycle, but they utilize a working fluid that's not water. It's some sort of, it could be a refrigerant or some organic-based compound. And they do this while the fluid is much more expensive. Water is free. But they do this because some of these other refrigerants, etc., will boil at a much lower temperature. And so if you have, say, you use waste heat back from an industrial process, you can run that flow of hot gas over a heat exchanger, and that heat exchanger can cause this organic fluid to boil at a much lower temperature than you can vaporize water. And so, the basic components of the cycle are the same. It's just a working fluid can be selected to match the temperature of the waste heat that you're trying to recover. So that's kind of what an organic Rankine cycle is all about. Okay, in fossil fuel plants, the energy required for vaporization originates in combustion of fuel. And so this is one of our diagrams. Figure 8.1 goes on, takes up about 2 pages. So we're going to have it this is out of that figure. And so your author divides different portions of the entire cycle and everything involved in the generation of electricity into different subsystems. And so he's showing subsystem A over here to be the boiler, and the combustion gases up to where they come out the top of the stack. So we show some fossil fuel, natural gas, or coal, probably could be oil coming in. We put in some air. We do combustion inside the boiler. Hot gases stack. That's what's going on in A. And then we transfer heat from the furnace region of the boiler into the working fluid. And so that heat crosses the boundary from A to B. And then inside B, this is the Rankine cycle. These four components comprise the simple Rankine cycle. And we'll talk more about that. Then we have just a shaft, and so we work. We have a torque being transmitted from subsystem B to C, which is just the electric generator. It's basically a big electric motor that operates in reverse. If you take an electric motor and spin the shaft, you get electricity out. You take an electric motor, put electricity in, you get torque out on this. So in the power plant configuration, the turbine produces the torque. It goes into the motor, and we get electricity, or the generator. We get electricity out the other side. And then, whoops, we have the heat rejection portion of the cycle. So this is the condenser, and so heat's rejected from there into, somehow we have to cool this. We have to condense this mostly vapor, very low pressure, low temperature vapor coming out of the turbine. And we use this is commonly lake water, river water from some large body that we can pump out, pump through here, fairly cool, take it back warmer, and go back to the lake, or this is showing the cooling temperature. We may not have a lake in this case. We just have some big tanks that contain water, and we pump it around. As we spray it out, some will evaporate, and then so this is a water vapor coming out of the top of the cooling tower. It's parabolic in shape, large, so that we don't have to have fans to induce the flow through the cooling tower. Okay, so that's figure A. So you notice for a nuclear power plant, the vaporization energy just comes from a nuclear reactor. And so if you look, everything from about here over to the right is basically the same picture as we have here. We have some sort of a heat exchanger where we are vaporizing the water. Then we have a turbine condenser pump, generator, and some sort of heat rejection system. There you go. This reactor just takes the place of the water. So we have our reactor. It has its internal recirculation, and then we have our feed water pump that comes over here. And this is the boiler. This is where the heat transfer occurs, and then we get our steam. And we do the same thing. And then we can go on, and we can look at, this is called a concentrating solar system, power tower. What they do, they usually have a bunch of mirrors on the ground, like in a semicircle around this tower. On the top of the tower, they have the boiler sets, and then these individual mirrors that are on the ground actually track the sun in their program. So they continually focus the maximum amount of solar radiation on that boiler up on top of the tower. It is usually filled with a molten salt that melts and vaporizes, doesn't vaporize, it just melts at a fairly high temperature. And then that liquid is circulated through a heat exchanger, and then the heat exchanger actually produces the steam. So we can talk more about that. But you notice, I mean, once we pick up energy, we make steam, and everything is pretty much the same. Now, temperatures and pressures do change based on energy stored. And I know most nuclear plants, the turbine rotation speed is 1,800 RPM. Coal plants, it's 3,600 RPM. So there are some, down to the nitty-gritty detail of the actual components, there are some differences. But in theory, the Rankine cycle it just needs heat input to make it go. And this is geothermal. So here the heat source could be hot water or steam. Is fairly deep within the earth. You see these things get implemented in areas where that energy is fairly close to the surface. Makes it easier to yet. I mean, if you have to drill 5 miles down through the Earth's crust to get to the high temperature, it makes it pretty unattractive economically. But at any rate, so if we have access to this hot water steam, we put it through the heat exchanger, we generate our steam, and then okay. So we're going to go back to A here, and we're going to talk more about these, subsystems, and then kind of talk about that. Subsystem B will be a primary interest to us. We can talk through those. I've already kind of done that. A provides the heat transfer of energy needed to vaporize the water, circulating B. This is combustion for a fossil fuel plant. Subsystem B, it develops the power, it generates the steam from the heat that comes in, steam through a turbine, and then we condense, and then we pump it back to complete. C is the power development, the generator that takes the torque from the turbine. And D, we have to condense that steam. We have to condense it because we need to use the same working. I think I've mentioned this in the past, but you just can't pump a vapor. And that becomes a compressor, and the amount of energy required to return a vapor through this thing is just way, way too much. This pump in this Rankine cycle, the pump energy would be probably 1.5, at most 3% of the turbine output. If that was a compressor, that could be 30, 40, 50, 60%. So it's just way too much. So in order to use the same working fluid around, which for purification, and there's lots of reasons that we have to condense. That's where the major energy loss is from this Rankine cycle in this condenser. Okay, so subsystem B, this is the Rankine cycle. So we're going to spend a lot of time here discussing this. We're going to show the working fluid work its way around. So that's okay. So we want to review the power cycle discussion in terms of the heat transfer, and just put all the cycle stuff in a box. We call it the system. And so we know from the first law requires that the network developed by the system of the power cycle equals net heat, net energy added by heat transfer. So the hot body, this could be the combustion furnaces, the combustion gases inside the furnace, inside the boiler, and then generates the really hot object, and then we transfer heat from that into the system, and then everything else is in the box, and then it comes out, and then this would represent the heat rejected in the condenser that goes to either the atmosphere or a lake or something like that. And so you see that the net work of the cycle is equal to the net heat, the heat in minus the heat out. Okay, and the thermal efficiency of the power cycle is the net work divided by the costly energy input, and that's right up here in the weather. That's what we spend our money for. We have to buy the gas for cooling, oil, whatever is combusted, and so that's the real expense of obtaining the energy to make the cycle go. Okay, second law of thermodynamics requires the thermal efficiency to be less than 100%, because we know the statement of the second law says that one of the statements says that we cannot transfer heat in and get 100% conversion to electricity. We must reject. Most of today's nuclear power plants have thermal efficiency ranging up to about 40%. 40% is a really good day for a simple plant. I would say the TVA plants would be down in the low 30s, especially the more emission control equipment we put in, the more they need typically fans operate. That's more parasitic for plant load, which reduces the net generation that goes out of the plant compared to a given amount of fuel input. Thermal efficiency tends to, this is a very important statement. You need to pay attention. Thermal efficiency tends to increase as the average temperature at which energy is added by heat transfer increases, and or the average temperature at which energy is rejected by heat transfer decreases. Well, that's interesting. So if you look at it, if we can increase the temperature here, we can increase the potential thermal efficiency. And from the Carnot cycle, if you fix some temperature and then increase the hot, keep the cold the same, you see that as I increase the hot, Carnot efficiency goes up. Well, that's wrong. The power industry knows this and has for a long time. But while it's interesting information, as you got higher and higher temperatures, which are possible from the combustion side, but you have all these materials, boiler tubes, steam pipes, turbines, and all this stuff, and there's some kind of a practical limit on the materials that these things are made out of, and the longevity of the equipment, and how long is it going to be before you have to replace it. So, in a lot of cases, the materials just don't support operating at higher temperature. As far as rejecting heat to a lower temperature, I mean, if you're rejecting heat to the atmosphere, to the air in the atmosphere, I mean, you get whatever temperature you get. I mean, you can't control that. Likewise, you can't control lake water temperature if you are rejecting heat to a lake. So, whereas theoretically, and in terms of our study of thermodynamics, we need to be very cognizant of this, and this will come up time and time again. That doesn't mean that practical operational sense that a plant can utilize this very much. Now, over time, materials are developed and operating temperatures can go up, which helps the efficiency. But that's, once you have a unit, it's made out of whatever it's made out of. And it's very expensive and not typically practical to replace large numbers of components. I say redo the whole boiler. It's just too expensive. Improved thermodynamic performance of power cycles is measured by increased thermal efficiency, for example, also accompanies reduction in irreversibilities or losses. Now, this is an area that can really be worked on. And so, if you can, reduce friction, reduce stray heat loss, reduce turbulence, reduce these dissipative effects, then by doing a better design, then you have some possibility here to actually make some improvements. The extent of improved power cycle performance is limited, however, by constraints imposed by thermodynamics and economics. So, if you ever visit a power plant, you'll see there's such massive structures, the boilers, the pumps, everything is so large. It costs a lot of money on the front end, and it limits the amount of retrofits that you can afford to do. You need, generally speaking, you keep it in operation. You have one particular plant component that's failing, you might look at replacing this. Sometimes turbine blades get replaced. They get nicked and dinged over time. And the new design of turbine blade may be a little more efficient than the older design because the turbine manufacturers are always striving to make them the best they can. Materials get better, manufacturing processes get better. And so it's possible in some cases to make improvements. Okay, let's see how we're doing here. We'll go about another 15 minutes here. Okay, Rankine cycle. So each unit of mass of water circulating through the interconnected components of subsystem heat undergoes thermodynamic cycle known as a Rankine cycle. There are four principal control volumes involving these components, and you see, so we've got a boiler, turbine, condenser, turbine, condenser, pump, and boiler. Pretty simple. And you see the order 1, 2, 3, 4. And in terms of these diagrams now in this chapter, all energy transfers by work and heat are positive in the directions of the arrows. On the schematic and energy balances are written accordingly. So whatever direction the arrow goes is considered positive, even though it could violate in some cases previously established sign conventions. Okay, the process is process 1 and 2. Vapor expands through the turbine, developing work. Process 2 to 3, vapor condenses to liquid through heat transfer to the cooling water or the cooling air, wherever it's being rejected to. Liquid, once we get it in the liquid state, we pump it back to the boiler, which requires work input. And then process 4 to 1, liquid's heated to saturation and evaporated in the boiler through heat transfer. So we've got a work process, creating work. We have a process involving heat transfer, which is the rejection of heat from the working fluid to the environment. 3, we have a work process from 3 to 4, where work is input to the pump in order to increase its pressure and get it back to the boiler. It's really the pump that establishes the highest pressure in the system. And process 4 to 1 is another heat transfer, where we're transferring heat from some high temperature source into the working fluid in order to produce the steam that we need. Okay, so when we write the first law, we're all familiar now with the first law for open systems. So each component is typically analyzed at steady state, unless you do some specialized problems. So typically we do steady state. Turbine and pump operate adiabatically. Typically, now you don't have to. You may have a specific problem at the back of the chapter, that we're working on that says no, assume this, but generally speaking, we assume these things are adiabatic and they're pretty heavily insulated, or they don't have enough surface area to transfer any heat from the working fluid. Kinetic potential energy changes are ignored. We all like that. It simplifies the equations. So applying the mass and energy rate balances we get for the turbine. So the specific work, the total work divided by the mass flow for a simple turbine is the enthalpy change. So that's kilojoules per kilogram through the turbine, or BTUs per pound mass through the turbine, whatever system of unit you're working in. Condenser, pretty simple. The amount of heat rejected per unit mass flowing is the enthalpy difference. The enthalpy in minus the enthalpy out for the working fluid. For the pump, the specific work for the pump, or total work divided by the mass flow rate. Power, really. The W dot, those are power. And is just the enthalpy difference. And for the boiler, guess what? The enthalpy difference. So the equations are not too bad. So that's the specific heat input of the boiler, the total rate of heat input divided by the mass flow. Performance parameters. So for thermal efficiency, we get that's the net work out of the cycle. So that's the turbine work minus the pump work divided by the rate of heat input in the boiler. And so we see that in That's the turbine work per unit mass minus the pump work per unit mass, divided by the boiler heat input per unit mass, and all the inputs then cancel from this, and we can substitute, or we can substitute what they would, uh, or we can substitute in the definitions of these in terms of the enthalpy. So we get H1 minus H2 per unit mass. That's the work out of the turbine. We're going to subtract off the work input required by the pump, and we're going to divide by the heat input per unit mass in the boiler. So we've got to find a bunch of enthalpies. Back work ratio is defined as what the pump needs divided by what the turbine produces. And so if we do it on a unit mass basis, W dot pump, the power of the pump, divided by the mass flow rate. And then likewise we do the same thing for the turbine. So the power produced by the turbine divided by the mass flow rate. And it just becomes the ratio of these enthalpies. Like I said, this is typically, the pump is a very small percent that's created by the turbine. Back work ratio is characteristic low for vapor power plants. For instance, in example 1, the power required by the pump is less than 1% of the power developed by the turbine. That's one of the real positive features of the Rankine cycle. It's easy to pump liquid, which is virtually incompressible. Okay, provided stage 1 through 4 fixed, equations 8.1 through 8.6 can be applied to determine the performance of a simple vapor power plant adhering to the Rankine cycle. So we're just going to problems actually determining the efficiencies. Since these equations are developed from mass and energy balances, they apply equally when irreversibilities are present and for idealized performance in the absence of such effects. So when you go back, when you use just the mass and energy balance, it doesn't matter as far as the equations are applicable, whether it's an ideal cycle or it's a real cycle that actually has losses and pressure drops and stray heat transfer and all of that stuff. We can define an ideal Rankine cycle, which provides a simple setting to study aspects of vapor performance. The ideal cycle adheres to the additional modeling assumptions. So when we say ideal, this is going to be the perfect frictional pressure drop or absent during flows through the boiler and condenser. So whatever pressure is into the boiler is out of the boiler, whatever pressure is in out of the pressure flows through the turbine and pump occur adiabatically and without irreversibility. So friction's out, and we don't have stray heat transfer and all that. Thus, they are isentropic. So we have an isentropic turbine, and we have no pressure drops. So those are some of the ideal Rankine cycle, which makes life a lot easier, makes the problem solutions quicker. Also makes them with results that don't necessarily coincide with anything you can see in the real world, but nonetheless, we get some sort of an ideal performance parameter. Okay, and I think we're going to stop here for this, and so this will conclude class for Tuesday. You can look over the solution to the test. That's about 40 minutes, and I'm not sure. I think it's someplace around 40 minutes here. So I'm going to stop recording, and I will be back in touch. I'm not sure if we're going to have in class maybe Thursday or not, but I'll let you know. So until later, hope everybody has a great day. Thank you.